All right, this last recap here is going to do limiting reactants again, same problem as before, but now we're going to do it to try to figure out how can we use a BCA table. And it's the same question. How much of this can we make? And which one of these is limiting? And which one of the excess one, how much of it is actually left over? So how do we do that? Well, we need to get these converted into moles, first off. Now, the stoichiometry can be done on the side for this, but you have to use a molar mass. This 4 doesn't mean anything yet, right? We only use those to go between chemicals, but 3.25 divided by the molar mass, 17.04 of ammonia, is going to give us 0.191. And these are all in moles. This chart is done in moles because what it does is it does all the mole ratios at the same time. So if we can start with moles, then we can figure out and kind of take the whole problem holistically and see what's actually happening. If we do that with oxygen, diatomic, 3.5 grams divided by 32 grams per mole, we get 0.11 moles. Okay. Let me do that to the right sig figs. It's 0.109. Okay, so what do we do here? Well, we have to figure out the change. We have none of these to begin with. And the coefficients now become the change. Minus 4x, minus 5x, plus 4x, and plus 6x. So we get these little algebra problems. And if we can figure out what x equals, then we can solve everything in this problem all at the same time. We can at least get it into moles. So we have to figure out what x equals. To do that, we have two possible solutions. The limiting reactant, we don't know which one it is yet, but the limiting reactant is going to go to 0. It will be either this one or this one, but it cannot be both. So you have two little algebra problems to see which one goes to 0. And really what this does is it's taking these coefficients and it's simplifying them. Because if we can solve them and compare them in a 1-to-1 ratio, then we know which number is smaller. So if I divide this by 4, I solve for x here, I will get this x value is going to be 0.0478. That is a possible answer. And then if I divide this one by 5 and solve for x, 0.109 minus 5x equals 0, rearrange that, solve for x, I will get 0.0219. Now I just got rid of the coefficients. I divided this by 4, I divided this by 5, and I get this 1-to-1 comparison. That's really useful. They're both in moles, so now I know which one's smaller. Which one's going to run out first? Well, we have less of this. This is my limiting reactant. This now means nothing. Okay, this means nothing. This is not going to go to 0. We found out that the oxygen is limiting, and this is excess. Because we simplified them into 1-to-1 and we had less oxygen. So we have to use that less oxygen. Once you figure that out, you kind of keep that up to the side, 0.0219. That is your x value, okay? You know that this is going to be gone. This goes to 0. You know that this is excess, and if you subtract 4x, plug that in. You know how much ammonia is left. Remember, this is in moles. You know how much NO you can make, it's 4x. You know how much water you can make, that's 6x. Now these are both in moles also. So you might need to do a little bit more to finish this problem, right? This might need to be converted back to grams. That's not hard, moles of ammonia to grams. This might need to be converted back to grams. This might need to be converted back to grams. I'll tell you in chapter 4, these answers might need to convert it to volumes, or we'll learn a new unit, molarities. How many moles can you get per liter? So depending on the context here, we can convert these different ways, But when we do this in moles and we reduce the coefficients, we can kind of figure out what's limiting. Then we can solve all the answers at once. I know how much I can make, and I know how much of the excess is left over, and then we can solve them all at the same time. So this is how BCA tables work. It's the general idea. It can go really quick once you get it down. But you do this chart here in moles to do all your bookkeeping and keep track of the coefficients all at once.